Hello, welcome back to Sri Sai Tech Edu YouTube channel, Read Lead Success. I'm already started with the subject network analysis and control systems. In that already the previous videos have done the first chapter, that is basic circuit elements. It is done, and network theorems also I started now the second chapter. In that we have already done the two videos on the two theorems, that is superposition theorem and the Thevenin's theorem. Now we will study the next theorem. Superposition theorem is done and Thevenin's theorem is also done. Today we will study Norton's theorem. Norton's theorem, we will see the statement: any two-terminal linear network containing energy sources or generators like current sources, the voltage source, and impedances can be replaced by an equivalent circuit consisting of a current source I dash in parallel with an admittance Y dash. Here it is a current source parallel with the admittance, whereas in the Thevenin's theorem, voltage source E dash is in series with the resistance. So here it is current source I dash in parallel with an admittance Y dash. The value of I dash is what? The short circuit current between the terminals of network. Whereas in Thevenin's theorem, it is E dash is the open circuit voltage. Here we are finding I dash, that is current in the short circuit current between the terminals of the network, and Y dash is the admittance measured between the terminals with all energy sources eliminated. We will eliminate all the energy sources and we calculate the admittance, but we eliminate the energy sources but not their admittance. The admittance will be calculated of all the energy sources. We just eliminate energy sources, that's it. Now we will see the proof. Proofs are very important in these theorems. They have asked in the question papers, previous question papers. So please do study the theorems. Thevenin's theorem also it is important. Superposition theorem is also important. Now we have another Norton's theorem. We will see the proof. There are two figures here. In figure 9.11a, terminals A can be replaced by figure 9.11b, provided if I dash is equals to E dash by Z dash. We can convert this to this. We can convert this network to this by connecting I dash in parallel with the impedance and the load current. So that to do that we need these equations, that is I dash is equals to V by R, or V is nothing but E dash, R is nothing but Z dash. Then 1 by Z dash, the inverse of impedance is the admittance, so Y dash, so E dash into Y dash. So in the circuit 9.11a, if you want to calculate the load current, first we will consider this circuit. We'll calculate the load current. If you want to load current at the ZR IR, then the total potential E dash by the total impedance, that is Z dash plus ZR. Then the next step what it is done is multiply and divide by Z dash. Then E dash by Z dash you will get I dash into Z dash by Z dash plus ZR. Why we want I. So in terms of I, if you want, it should be divided by Z dash. To eliminate this Z dash, you need to again multiply into Z dash. Okay, after that IR is equals to, if you consider Z dash is nothing but 1 by Y dash, we know, and ZR is 1 by YR. So if you replace in this equation, if you write this, then what you get is then what you get is E dash into Y dash into YR by Y dash plus YR. If you take LCM and do the change, if you take from numerator to denominator, and if you do that, then you will get this equation. Then E dash into Y dash, you know it as I dash, you take as I dash, then into YR by Y dash plus YR. You got, by using the first figure, you got I dash IR, the load current at the short circuit, that is the load current, load resistance is this. Now we will see the second figure. In the second figure 9.11b, the load current how we will calculate. How we can calculate is that you want load current at this resistance. So what we will do, the total current is I, and multiply with the opposite resistance, that is Z dash by Z dash plus ZR. If you substitute Z dash is equals to 1 by Y dash and ZR is equals to 1 by IR, then you will get I dash is equals to YR by Y dash plus YR. If you see, the load currents calculating with this circuit and this circuit are similar. We get the same values. So that is what it is telling, that from these 9.33 to 9.36 equation, the load current IR dash may be equal to IR in the circuits. If in circuit figure 9.8, if I dash is equals to E dash by Z dash, if this is accepted, if this is correct, then the figure, these two figures load current is same, they are telling in the sentence. Then we can say that 9.11A and 9.11B circuits are equivalent. This is the Norton's theorem. And the proof, you need to, if they ask Norton's theorem proof, you need to write that statement what I have mentioned in the board and write this proof. Okay, now we'll go to the sums. Using repeated source transformations determines the Norton equivalent of the highlighted network. Then what we will do, first source transformation we need to do. To get the source transformation, I and R is there in parallel. So V can be converted into V. 10 volts we will get. We'll see how it is going to look. It is the how it looks. And for Norton's theorem, what we do is we short circuit the load resistance. In Thevenin's theorem, we open circuit this load resistance and we find the open circuit voltage. But here we are going to short circuit the resistance. We remove that resistance by short circuiting it and we find the Norton's current. Okay, and if you see the same sum I've solved for the Thevenin's theorem also in the previous video, so that you'll know the difference between the Norton's theorem and the Thevenin's theorem, how to do the same sum. What is the difference? If you short circuited, there is a resistance parallel, that is 10 ohm. You can remove that resistance. Why? Because only one resistance is in parallel with the short circuit, so you can remove that resistance. Then if you add them, why? Because they are in series, 10 ohms, you can find the short circuit current, that is IN, that is short circuit current ISC, that is equals to IN is equals to voltage V by R, 10 by 10 you will get as 1 ampere. And after that you need what? Resistance, Norton's resistance. To get Norton's resistance, take the 2 ohms and remove all the energy sources. That is 10 voltage source is short circuited. If you short circuited, then you get 2 and 8 as in series, and that is in turn parallel with 10 ohm. And finding Thevenin's resistance or Norton's resistance is same. We see through the open terminals and find the resistance. Only the resistance will be there in the network. After this 10 and 10 are in parallel, so you get as Rn is equals to 5 ohms. After getting it, you need to draw in this way. That is, you should, as you remove the load resistance, you should write that back, and current what you got, 1 ampere in parallel with the 5 ohms resistance need to be mentioned. You'll see the next question. Find the Norton equivalent circuit for the network phased by the 1 kilo ohm. For the network phased by the 1 kilo ohm means this is the load resistance. So we can remove that resistance and short circuit it and find the Norton's current. If you short circuit it, there are 1 voltage source and current source and 2 kilo ohm, 3 kilo ohm. If you see the circuit, you can use superposition theorem to find the current. If you don't know how to calculate superposition, how to do superposition, there is a video on superposition that I have done previously. You can watch that and you can understand. Anyway, I'll explain here. If you want more information, you can watch it. In superposition theorem, what we do, we first eliminate one source and calculate the current by this source, and then we retain now this current source and remove this voltage source and find the current and add on both to get the whole current. First we will eliminate the current source, then you will get IN dash, that is total voltage by 2 and 3 will be in series, so you will get 2k plus 3k, that is 0.8 milliamperes. Then you will remove now voltage source. By short circuiting it, the current source will be retained. To get the current, we want current at the short circuited, that is at 3 kilo ohm. So if you want that, then what we will do, you use current divider rule. IN double dash is equals to total current is 2 milli into, you will multiply the opposite resistance for current divider rule into 2k by 3k plus 2k. You will get IN double dash as 0.8 milliamperes. For getting total IN of separately by current source and the voltage source, you will get is 0.8 plus 0.8, that is 1.6 milliamperes. After getting IN, we are left with RN. To get RN, you remove all the sources and keep only the resistances, 2K and 3K. If you see these both are in series, you will get 5 kilo ohm. After getting the RN and the IN, you need to draw the circuit back by again connecting the 1 kilo ohm that we have removed initially, that is load resistance, and we need to add this IN, the Norton's current 1.6 milliamperes in parallel with the 5 kilo ohm. Now we'll go to the next question. Determine the Norton's equivalent of the circuit. If you see, this is the circuit. They have already given the open circuit. We need to short circuit these open terminals to find the current IN. We will short circuit it. Anyway, this point here, if you connect also here, if you connect this point also same. So I have connected that 5 kilo ohm to this point and took this as VA node and applied KCL. By applying KCL, you will get, if you think this as the current incoming, as we are taking opposite to the current flowing, we will take as -7. Summation of incoming nodes, summation of outgoing is equal to summation of outgoing nodes is VA by minus 3 by 2K and VA by 5K and VA by 1K. Okay, after doing this, then if you calculate, you will get a equation. Then VA will be minus 3.235. Initially we got VA, but we want IN. To get IN is equals to IN is at the short circuit side, we find the IN. So IN current, what it is there, voltage VA by R is what, 1 kilo. If you substitute, then you will get IN as minus 3.235 milliamperes. Then now we want RN. For getting RN, we eliminate all the sources, only resistance will be retained, 2K, 5K and 1K. If you see, 2K and 5K are in parallel and in turn they are in series with 1 kilo ohm. Then if you find 2K, 5K in parallel resistance value and add with 1K, you will get RN is equals to 2.429 kilo ohms. Okay, after finding this, you will draw the equation, will draw IN parallel with the RN values. This last step is compulsory. This step is compulsory. With respect to the circuit depicted in figure, obtain the Norton equivalent of the network RL. They want Norton equivalent of the network RL. So short circuit at that point. So we will see now, short circuited, then a 9 volt, 2 ohm, 1 ohm, 3 ohm is same. You want current at this point. As is the circuit is simple, I have done in a different way. If you see, this voltage source is in series with the 2 ohms. So you can convert into current source. Current source will be V by R, that is 9 by 2 amperes in parallel with the 2 ohm. Again this 2 ohm is parallel with 3 ohm. So 2 ohm parallel with 3 ohm and 1 ohm. After that, you will get 4.5 amperes in parallel with 1.2 ohms and 1 ohm. If you want, the current should be, the Norton's current is calculated in this 1 ohm resistance. That is short circuited. Where we have short circuited, we need to find the Norton's current. So here it 1 ohm. To get the Norton's current, what we need to do, the total current 4.5 into the opposite resistance 1.2 by 1 plus 1.2. This is current dividing rule. We will get IN as 2.4 amperes. Now we got IN. We want RN now. To get RN, what we need to do, eliminate all the energy sources, only retain the resistances. Then if you see, 2 is parallel with 3 ohms. 2 is parallel with 3 ohms and it in turn series with the 1 ohm by the circuit. Then if you calculate, you will get 1.2 plus 1, that is 2.2 ohms. After getting RN and IN, you need to draw the circuit by putting this IN parallel to the RN value what you got. Again bring back the resistance if you have removed and connect it to here, the load resistance. If there is no load resistance, no need to connect. If there is some load resistance RL or some 1 kilo ohm if you removed, then you need to connect it back. Determine the Norton equivalent of the circuit drawn in figure as seen by terminals A and B. Here I have took a dependent source so that you will understand when dependent source how to calculate. First initially we will short circuit it, the open terminals. Let us short circuit the open terminals. If you short circuit the open terminals, you can see that this resistance is in parallel with the short circuit. You can remove that short circuit, resistance. If you remove that resistance, this is a circuit how it looks. Then after that, if you see the current 700 milliamperes is looking like a super mesh that I have indicated by the dotted lines, so that you can remove that current, but the mesh currents you can take it as Ix and I2, but the currents you need not to be changed, but that just that current source can be removed and apply KVL to mesh 1. In mesh 1, minus 500 Ix plus 2 Ix plus 2500 I2. You need to consider this also. Why? Because we are temporarily removing this super mesh current, and later on we will add it back anyways. After that, if you don't know mesh analysis, please watch my previous videos which is separately for mesh analysis. You will understand how I am doing this. Then if you see at I2, if you want minus I2 minus Ix is equal to 0.7, you will get the another equation. As we have removed, we have added it back and took the current at this point. So solving 1 and 2, what you will get? You will get I2, that is Norton current at the short circuit, that is nothing but I2 current. So I2 is equals to IN. You will get as minus 116.3 milliamperes. We got IN. Now we want RN. To get RN, we will connect this IN, not IN, I'm sorry. To get the resistances, we remove the dependent sources and the energy sources. Only we'll keep the resistances. After keeping the resistances, if you see, these two are in series, and that in turn they are 1500. It is in parallel. So 500 plus 2500 is 3000. Is in parallel with 1500. You will get RN as 1000. So after getting an IN and RN, what we need to do? We need to draw the circuit. How to draw the circuit? IN should be in parallel with RN. IN is minus 116.3 milliamperes with resistance RN with at the open terminals A and B. There is no load resistance or something, no need to draw. So I have done different types of sums so that it will be easy for you. You can solve still more sums, different sums, so that it will be easy for your final exam. These are the practice questions with the answers. You can solve them. If you have any doubt in the video as well as in the practice questions, please do comment so that I will solve. If you have any other doubts also, you can please comment. So I'm stopping the video here. We are already done now with the superposition theorem, Thevenin's theorem and Norton's theorem. We are only left with the maximum power transfer theorem. We'll complete, if we complete maximum power transfer theorem, we complete the module 1 and as well as the second chapter of the module 1. So whole module 1 will be completed with one more video, that is maximum power transfer theorem topic. So I'm stopping the video now here. Thank you from Sri Sai Tech Edu YouTube channel. Read, lead, success. Keep reading.